Hello everyone. Today I'd like to share something that I've noticed through my career. I actually work as a deployment and integration expert at WCHAN, which gives me the opportunity to interact with many different teams, technologies, engineers. Over the years, I've worked with the operational teams, developers, system administrators, etc. One thing has consistently surprised me. Many experienced engineers still struggle to correctly interpret basic system information. And one of the best example I can say of this is the top command. Now, don't get me wrong, most people know how to run top. The problem is that many people don't really know how to read it. I've met engineers with more than 10, 15 years of experience who look at top output, immediately identify a problem, and start raising alarms about something that is actually completely normal. It sounds strange, I know, but it happened, and more often than you think it is. The reality is that misunderstanding around CPU usage, memory consumption, load averages, process priorities, threads, and many other metrics can lead to incorrect conclusions, unnecessary troubleshooting effort, and sometimes even wrong architectural decisions. So, in this short video, I'm not going to explain everything, of course, in one single video. This is might take more than it should be. You can find the information anyway in countless tutorial online. Instead, I want to focus on the things that every engineer should understand, the concepts that are frequently misunderstood, and that often lead to confusion during troubleshooting sessions and maybe wasting the support engineers that who are trying to help you. So, my goals is simple: help you avoid some of the most common mistakes I see in the field and gives you a practical way to interpret what top is really telling you, so you don't go to through a route that is not going to lead you anyways. So let's start with the real example. For example, I have this service. Let's see what we have here. For example, let's say number of virtual CPU, we have 32. Okay, free age. Those are the, when I start first time access a server, I usually see those before top. So we have 62 gig and we have 34 gig of RAM is used. The free only 2 gig, or you might say 2 gig of RAM. It's the server is running out. But actually, as you can see here, we have the buffer is 26, so the available memory is 23 gig of RAM. So let's see top, which is the main goal in this session to understand what the field really means. So the problem is that some engineers, let's say, even experienced one, like the last time, I think it was 2 days ago, I was interacting with someone, and he was really concerned about the vert, which is actually people saying that this column means the worst case scenario, which is pretty accurate. What does that mean? So let's take a screenshot here. So okay, this is the virtual field, vert field. Okay. So for example, let's see the user DMC here. The user DMC and the vert column is 39.2 gig, which is actually what I was saying. The guy told me that there is a problem. This services is eating the memory, and yeah, we need to know why. And actually, let me start from the beginning. Let's say that there is a process P1 here. Let's say P1. And this process is asking the OS, please give me, let's say, the OS, let's say 2 gig. Okay, what really happened? You think the OS is going to go to the RAM and just give it 2 gig. No, what's really happened, the OS is saying, okay, you need 2 gig. I promise you, I give you my word that I'm going to give you this 2 gig. 2 gig, what is this? And sorry for my writing. Okay, I promise you, I'm going to give you 2 gig. So this is just a promise. Okay, you have your 2 gig. Okay, so the process actually it is using something called alloc family. I think it is maybe 2L. Anyway, alloc, yeah, 2L, definitely. Or let's say mmap. They both serve different purposes. Mmap is for shemam. Mmap. Okay. So when the process asks the OS is going to use alloc or mmap families and is going to ask for 2 gig, the OS is going to respond, okay, I promise you, I give you my word that I'm going to give you this 2 gig. And this is what you see here. It doesn't mean that you have this 39 gig on the ship, but I promise you I'm going to give you this memory. So when this memory is going to be taken from the RAM, taken from the RAM uh, exactly is when the process start touching this allocated memory or the mmap. Okay, so when the process start to touching the memory, is going to read or write from this memory. There is something called, okay, the process is going to do a TLB lookup, TLB lookup, TLB, and there is page fault happen. When the page fault happen, the system is going to send a request. The process is going to send a request to the OS, the OS, and the OS is going to take some of the memory, the 2 gig that the process is asking for, and start touching uh, this memory. Of course, there is some exceptions. Let's say in Java application, there is value. I don't remember exactly what it is right now, but you can look in the internet. Is going to pre-touch the memory when the process is going to ask for it. But this is not the default behavior. Okay, so when it's going to ask for 2 gig, the system, the OS is going immediately touch this memory. But this is not, as I said, is the default behavior. This is how things happen. Okay, so as I said, this is the worst case scenario, and it's actually is going to include even the swap, etc. So it's not pure memory. So what is actually the hard, let's say the taken from the RAM or the chip exactly? Usually it is the resident memory, but there is something here that you need to be aware of. So, because sometimes, let's say you have 48 gig of RAM, okay, and you do calculate this column, you find out that this one, let's say, is 50 something, let's say 52 or something, or maybe 49, let's say 51. So you say how it is taken 51 and I only have 48. This must be wrong. Actually, there is something you need to know also. That the resident memory actually including something called the shared memory or shared libraries. Let's say your application, for example, is using glibc, glibc, okay, and this library is going to be loaded from the disk. Let's say it's going to take, I don't know, maybe, let's say, I really don't know how much this is going to take, but let's say it's 50 meg, okay, maybe more. This 50 meg, imagine, because there is so many applications that use this glibc, but imagine your application, every time an application or a process asks for glibc, imagine the OS is going to take this glibc from text from the disk and put it here in the RAM. This is going to, of course, to take a lot of memory, and this is not practical. So what's really happened? For example, when this service DMC asking for a shared library, the OS is going to put it in one place here in the memory, and every time there is a process or a thread asking for that shared library, is going to be pointed to that yeah, to that part of the memory. So let me show you something here. Maybe you can see it yourself. Okay, why I did that, I don't know. Anyway, let's show the thread. Okay, okay, let's take this. So as you can see, for example, we took a DMC here. For every time I see DMC, the shared library is the same. Those two and those and those. So those actually are included here in here, yeah, and the resident memory. That's why you see the same value is repeated again and again and again. Okay, so um, if we go back here, the next one is, let me take this away. The next one is the state. The state, there is I think 4 state as far as I can remember, but the most important one we have run, you'll see it R like here, which means runnable. Okay, I'm not going to write it. And there is sleep. Runnable means that this process is either in the CPU running or it is in the queue waiting for its time to be it is ready to be scheduled on the CPU to run. Sorry. So there is this also S, which means sleep, and there is another type of sleep called D. This one is very important because the problem is if the process is not running and it is sleeping, that's mean that it is not taking resources. The problem is that if it is in D state, which means that it is uninterruptible. You can't cancel this process, you can't interrupt it because it is waiting for some data, for example, let's say some data, and if it is not, if you interrupt it, is going to maybe ruin the application or is going to crash. That's why it is in this state, you can interrupt it. The problem is that when you see the D state, you will find out that there is not every time, but sometime when you have so much of those D state, you'll see that the load average here, it is pretty high. How you know the load average is pretty high? For example, here, usually I'm just giving you some tips. If you check, as I told you, and proc, you find out at 32, and you check here at the top, you see that the load average is going beyond, let's say 50 or twice or more of 64 or more of the number of CPU. It's not a rule, but usually this is how it happens. If you find out that this is more than 64 or it is around 64, that means that you have resources shortage, and you need to check why. Usually there is you have a disk issue, you have a network issue, you have interrupted issue. Sometimes there is in NOMA system. Okay, I don't want to go there. Anyway, you have to check the load average. If there is an issue, you can check why. Okay, so let's go back here. Mm, yeah. Um, mhm, 2 days ago, as I said, there is an engineer raised an issue here. He said that the memory is too high here. He's talking from the birth. As I told you, this one is not relative to you, unless you are enabling overcommit. Maybe that's a different story. But 90% of the time, I don't want to give absolute numbers here. You're not going, but you're not going to need to check this value. It's not interested to you. Usually you check this one. And be alarmed that the resident is also including this shared libraries and shemam. The state, as I told you, there is four state, three which are the important ones. The runnable, which is on the CPU or in the queue waiting for its time to run. It is ready to be running on the CPU. The S, which is sleeping, maybe it did its jobs and it is there is a context switching happen and it is out waiting for its time, or maybe it is in this state, something it is asking for data for example from the disk. It's not usually disk related. It could be another issue related to ERC, for example, interrupting let's say it could be hardware or software ERC. Yeah, let's say, but most of the time it is, for example, asking for data from the disk. But this time, but the disk, for example, load is too high, so there is latency here, and it is taking too much time to go to the process. This is usually what happens, but it's not a rule here. Okay. Anyway, yeah, as I said, he raised this issue. He said that it is the vert is too high, then this DMC is hungry, his memory hungry, and there is an issue here. We need to check why. And actually, as I said, it wasn't. This one is not really what is in the memory. And he raised another issue. He said that there is here, it was, let's see how much this one is taken here. If we enable the the thread, it is low. Oh, I didn't do it. Okay, the H, still not much. But yeah, basically, you see a number here. It was exactly 154 point something. I don't remember, but this is the main thing. And he said that this application also is CPU is burning the CPU. The problem is that this 154 is just one core and a half. Imagine in 32 core. So he's raising an issue that doesn't exist. So this application was eating 1.5 core during the peak, and he was complaining about it. So this also explain the CPU part. The memory, it is just the memory percentage, and this one is just the command that it is running this process. Let me show you. You can go here, press C. Let's say C. As you can see, the full command. But this one is not interesting to me. What I really do, I always, and I say always, enable the WCHAN, which is a waiting channel. Because, as I said, let me do this. Okay, let's take it up. Okay, let's put it here. Okay, this one is WCHAN. Let's take this. Okay, no problem. It's okay. So, as I said, there is four states. The most important are three: the runnable, the sleep, the D state. Here will reside the headache. Okay, so sometime when there is an application or a process or a thread that is sleeping, asking for, let's say, ask for the disk, what's going to happen? The process is going to sleep on the kernel because the process shouldn't access the hardware. You're going to sleep for the kernel, and the kernel is going to do the job for you. Okay, so to understand exactly what happened, why this process is sleeping, this is just a general case. Why the process is sleeping? you can check the WCHAN. The kernel actually what the kernel is doing is going to give this process a label called WCHAN. Why it is in waiting channel WCHAN. Okay, it's going to give it the label, which is going to explain to you what this process is sleeping on. As you can see here, do able is usually waiting for let's say there is a socket waiting for data coming from another service or yeah, something like this. So it is waiting for some data. Okay, so in this way you can understand what is the process sleeping on, because you need to know why it is not running. This is from a performance engineer standpoint, you have to understand why this process or this thread is not running on the CPU. If it's not running, we need to know why it is not running. Okay. Um, yeah, there is something else I want to share here. Maybe it's not as important, or because it needs actually more time to be explained, but to just give you an idea here, as you can see, the priority and the nice time. The nice time is just how nice this process is. Is it hungry for to be scheduled, or it is nice enough to wait and to wait for other process to work and then work when there is a slot for it. Okay, as you can see here, there is minus 20, 0, etc. 19, 19, which means that this process doesn't mean a lot of time. Yeah, this is very nice. And the priority actually is just a number presented to you, so you can understand your application. But actually, the scheduler is using the nice value, and is going to calculate something called wait, and the wait is going to be used for uh, the what it called the VRAN time. Yeah, VRAN time. VRAN time actually what it means is when the scheduler try to do like a tree to calculate. Um, let's say this one is 19. This one, let's say, is 500, etc. So it's going to use this tree to calculate this tree to understand. For example, this one is only the 19, so this one didn't have enough time on the CPU, so it must be the first one to be scheduled on the CPU. There is too much into it, but this is basically, yeah, this is basically how it works. Yeah. Uh, as I said, the load average, we talk about it. There is zombie. So basically, this is the most important things that you might take from top. You have to understand the difference between vert and resident, what is shared memory, how to interpret the CPU. As you can see here, there is 99. Someone see 99 is going to be alarmed and say, oh, this process is taking too much. This is unison, but actually this is less than one core, almost one core. Okay. Um, yeah. So this is top command. The most important columns that I can show to you, so you can understand. There is only one option I want to show you, because this is sometime when you have in one server too many process and you want to just look what interesting to you. Just click I. As you can see, those are all the user application that you have most of the time, what's interesting to you. Okay. Hopefully this video was helpful for you, and hopefully you don't make those mistakes. But if you do, now you know. Now you know. Okay. Thank you. Bye.